All right, so with those tools added to one's toolkit, let's actually consider and reveal what's been going on underneath the hood since last week. So this was the mental model we proposed for last week, whereby when you write source code in a language like C, it's not something that the computer itself understands natively, because computers, we saw, only understand zeros and ones, aka machine code. So the compiler is the program that we use to convert your source code to the machine's code, from C to zeros and one in this case. More generally, a compiler is just a program that translates one language to another. And in this case, we're going from source code to machine code. So let's consider what's really happening. And indeed, this is among the goals of this week, is to take a look at a lower level so that when you encounter more interesting, more challenging problems, you'll understand from so-called first principles what the computer is actually doing and supposed to do, so you can deductively figure things out for yourself and generally not view computers as like magic, or I don't know how this works. You'll have a fairly bottom-up sense of how everything works by term's end inside of any computer, laptop, desktop, phone, or the like these days. So here's the simplest of programs that we wrote last week, even though there's a lot of syntactic complexity, as we've seen. The goal is to get it to machine code, these here zeros and ones. So how has that been happening when you just run make since last week? Well, these are the two commands that we've typically run after creating a file like hello.c. We then compile it with make hello, and then we run it with /hello. So let's give ourselves this starting point real quick, just so that we have an example in mind of exactly what it is we're compiling. So let me go back to VS Code here, close out buggy.c, and let's create a new file just like last week called hello.c, inside of which is our old friend, standardio.h, int main void, and then inside of this, we'll keep it simple, just printing out hello, comma, world, which again is my source code in C. How do I now actually compile that? Well, of course, I can go down to my terminal window, make hello, /hello, and we're off and running. So it was a bit of a white lie for me to let you think, though, that last week the compiler itself is called make. Make is a command that literally makes your program. It makes it by compiling it, but make is not technically the compiler. If we really want to get nitpicky, the compiler you've been using is actually called Clang for C language. And this is a very popular compiler, freely available, open source, so to speak. You can even look at the code other humans wrote to create the compiler online. And what make is really doing for us is essentially automating this command. So all this time, I could have just run clang space hello.c, but the default file name from Clang, the compiler, weirdly and for historical reasons, is not going to be hello, as you would hope. It's going to be a.out for assembler output. And we don't do this in the in week 1 of the class, because this just makes things unnecessarily complex that we're adding some random name that you just have to know to type. However, we can do this now as follows. Let me go back to VS Code here. And let me clear my terminal and type ls, and we'll see everything we've created thus far. Buggy.c, which when I compiled it, I got buggy. And hello.c, which I just wrote, and when I compiled it, I got hello. Let's do this command now manually, though. Let's use clang on hello.c and hit enter. That too seems to work. But if I now type ls, you'll see a third program specifically called a.out, which happens to be the same as hello. It just is using the default name instead of my custom name, hello. But if I do /a.out, indeed, that too will work. But the reason we don't do that, certainly in the first week of the course, is that things get a little annoying or sort of escalate quickly thereafter. So let me go ahead and change this program as we've done a few times already. Let me include CS50.h so that we get access to like getString. Let me do string name equals getString, quote unquote, what's your name, question mark, close quote. And then down here, just like before, let me add my %s and add in my name. So I did that super quickly, but it's the same program we wrote a few minutes ago, and it's the same one we wrote last week. What happens now, though, is as follows. If I now try to do clang hello.c enter, I actually get an error message. This one perhaps more cryptic than most. Somehow or other, I have this error. Linker command failed with exit code 1 because of an undefined reference to getString. Now, in the past, when we've seen undefined or really undeclared mentions of getString, the problem was just with missing this line. This line is clearly here. But the catch is I'm getting this error message now because when I run clang of hello.c, I'm just assuming that Clang knows where to find the CS50 version of getString, and that is not the case. Technically, if I want the compiler to compile this code for me, what I'm actually going to have to do is this. Let me go back to my terminal window here, and I'm going to say clang hello.c, but I'm then going to specify -l CS50, which is cryptic at first glance, but this is telling the compiler to link in the CS50 library so that it knows what the zeros and ones are that belong to the getString function. Long story short, if I hit enter now, the error message has gone away. If I type ls, I've still got a.out, but it's a new version thereof. And if I do /a.out, now I see the new behavior where I can type in my name and see hello, comma, David. Now, this is getting a little stupid that I keep using a.out. We can change that as well. In fact, these commands, as we're starting to see, support what are called command line arguments. And a lot of the programs we've run already take command line arguments. When we run code space hello.c, the so-called command line argument to code is hello.c. When I run make hello, the command line argument to make is hello. In other words, the command line arguments to a program are all of the words you're typing in your terminal after the name of the program itself, whether it's make or whether it's code or anything else. So this is to say, what I just ran clang of hello.c -lcs50, I was passing in two command line arguments, hello.c, which is the code I want to compile, and -lcs50, which means use the CS50 library, please. But I can add another to the mix. I can actually do something like this, whereby I do clang -o hello, then I can do hello.c, and then -l CS50 enter. Now that too seems to work. And if I type ls, well, I've got all the same programs as before. So let's go ahead and get rid of those to make clear what's going on. I'm going to remove a.out. I'm going to remove hello. And just for good measure, I'll remove buggy as well, so that all I have left in this folder is source code. So if I type ls, there's my two files. Let's do this again. Clang -o hello, hello.c -l CS50. Enter. Now if I type ls, I don't see a.out anymore, because apparently, according to the documentation for clang, the actual compiler, if you pass -o as a command line argument followed by another word of your choice, you can name the program anything you want without having to resort to mv or clicking on it and typing a new name in manually. So if I now do /hello, I see the exact same version where it's just asking me for my name and then printing it out. But long story short, the whole point of this exercise is that like running commands like this quickly gets very tedious. You have to remember like the order in which to do it, what the command line argument. I mean, this is just stupid waste of time. Typically, certainly in week 1 of the course, to have to memorize these kinds of magical commands to get things working. But for now, know that when you run make, it's essentially automating all of that for you and making it as simple semantically as make hello or make buggy. But what's really happening is the make command, because of the way we've configured cs50.dev for you, is doing all of this behind the scenes. And it's not that magical. This just means change the file name to hello when you compile it. This just means compile this code. And this just means use the CS50 library. Like, that's all. But that message about linking something in, there's something juicy going on there such that make is, in fact, helping us sort of solve a whole bunch of problems when we compile. And in fact, let me propose that if we take a step back and look at some of the actual code that we're compiling, let's consider like what we actually mean by compiling. Yes, it's the case that to compile our code means to go from source code to machine code. But technically, there's a few more steps involved. Technically, when you compile your code, that's sort of become the industry term of art that really is referring to 4 separate processes, all of which are happening in succession automatically, but each of which is doing a different thing. So just once, let's walk through these several steps. So what is this pre-processing step? So consider this program here, which we wrote in brief last week. We've got include standard.io.h, which is there because we want to be able to use printf ultimately. We've then got a prototype for this meow function, and the meow function does this. All it does is print out, quote unquote, meow, followed by a new line, takes no input, returns no return values. The main function now has a for loop, iterates 3 times, each time calling the meow function. And we saw this already earlier today. This line of code here, the so-called prototype, is necessary because we need to tell the compiler that meow exists before we actually use it here, especially if I don't get around to implementing it until later. So this copy-paste of that first line of code, a so-called prototype, solved that problem. This is what the header files are essentially doing for us. Before I use printf down here, the compiler needs to know what it is, what its inputs are, what its outputs are. Turns out the prototype for printf is going to be in standard io.h. And that's what that line of code has been doing for us all this time. In fact, let's take a simpler example that we keep using here, whereby I'm including CS50.h and standard io.h. And I'm using the CS50 getString function to get someone's name and put it in a variable called name. And then I'm printing out hello, comma, such and such. What's going on now when I pre-process this file by running make, which in turn runs clang? Well, the compiler finds on the server's hard drive the file called CS50.h, goes inside, and essentially copies and pastes its contents into my own code. Meanwhile, such that we get the prototype there for getString. And we haven't seen this yet, but it stands to reason that all this time using printf, we've been passing in a prompt, like what's your name, and we've been getting back a string. What's inside the parentheses, recall, is the input. What's before the function name is the output, the so-called return value. What about standard io.h? It's in that file that printf's prototype is. So essentially what the compiler does when pre-processing this file is it finds standard io.h somewhere on the server's hard drive, goes inside, and copy and pastes those relevant lines of code into my code as well. It's to avoid me having to do all of that myself, find the file, copy, paste it, or manually type out the prototype. These preprocessor directives just automate all of that tedium. So what this effectively has at the top of my code after the file has been pre-processed is all of those hash symbols, followed by include, are changed to contain the actual contents of those header files. Now the compiler knows what getString is all about and what printf is all about. That then is the pre-processing step. What does compiling technically mean? Compiling means taking that pre-processed code, which again looks a little something like this, and convert it into something called assembly code. And we won't spend much time in this class on assembly code, but this is how programmers used to write code. Before there was C, before there was Python and Java and all of these other modern languages, programmers were writing code like this. Before this existed, they were programming zeros and ones into the earliest of mainframe computers using punch cards and other technologies, like literally sheets of paper with holes in them. Not very fun, very tedious, so the world invented this. Also not very fun, very tedious, so the world invented C. Not that much fun, so the world invented Python and so forth. We continue to sort of evolve as a species with code. But the compiler technically takes your preprocessed source code and converts it into something that looks like this, cryptic, and that's to be expected, but there are some familiar phrases. There's mention of main, there's mention of getString, there's mention of printf. And there's a bunch of other things, move and push and XOR and call and these other commands here. These are the assembly instructions. Those are the lowest level instructions that the CPU inside of a computer understands. CPU is the central processing unit, the thing by Intel or AMD or Apple or other companies. Those are the lowest level commands that the actual hardware inside of the computer understand. It's just nice to be able to write words like main and for and printf than it would be to run these much more arcane commands that you'd have to look up in a manual. So compiling just takes C code and makes it a lower level type of code called assembly. When I said a.out means assembler output, that's why. Inside of that file is essentially the output of an assembler. All right, we're almost there. What does it mean to assemble a program, which is step 3 of the compilation process? That means converting assembly code to the actual zeros and ones we keep talking about. So if the file is called hello.c, when that file is assembled, the assembly code becomes the zeros and ones for your code in hello.c. But your code is not everything that composes your final program. Your code from hello.c has to be combined with code from CS50 library, from the standard IO library that other humans wrote. I and the team wrote the CS50 code. Other humans in the world wrote the printf code in standard IO. So essentially, the fourth and final step is to link all of those zeros and ones together. Somewhere on the server, there is not just the header file, CS50.h and standard io.h, but your code, hello.c, our code, CS50.c, and the code that contains printf's own implementation. Bit of a white lie. It's technically not called standard io.c, but the point remains ultimately the same. So these files have already been compiled for you in advance. This is your code. What the assembly process does is it combines all of that into zeros and ones, and then all 3 chunks of zeros and ones are linked together. So if you think back to when I tried compiling the code without -LCS50, there was some mention of linker. Linking just means the computer did not know how to link your code with CS50's code because we were missing -LCS50, which tells the compiler to go find it somewhere on the hard drive. And the final step then of linking is to combine all of those zeros and ones into one bigger blob of zeros and ones, and that's what's inside your hello program that you can execute. So long story short, these 4 steps are what's been happening ever since the start of last week. Pre-processing, compiling, assembly, and linking. But thankfully, the world of programmers generally just treats all 4 of these steps as what we know now as compiling. It's just a lot easier to say compile and not worry about those lower level details. But that might reveal better to you what all of these error messages mean when you see hints of this kind of terminology. Whew. Questions on any and all of that? From here on out, we're going to go higher level than lower.